Hello. Um, this is Prof. Nanius, and what I like to do here is to go over the proof and with using other mathematical facts of the following formula: the derivative of x to the r is equal to r x to the r minus 1 for all real r. Now, we'll go ahead get started here. And let's see this. And here we go. So that's what we like to do right here to show that this is true. So the first step, first step one, is to use, let's prove this for r, a non-negative integer. That is 0, 1, 2, etc. Now, if you wish to take the derivative of x to the 0, that's, of course, the derivative of x to the first of 1, because x to the 0 is 1, and that is, in fact, 0, which is 0x to the 0 minus 1, right? So no problems there. Well, I guess you could be pedantic and say that technically 1 over x is not defined as 0, but yeah, not too worried about that. So let's just choose some integer that's not 0. So let's figure out what the derivative of x to the n is, where n is not 0. Well, by the limit definition, as h goes to infinity, x goes to 0, sorry, of x plus h to the n minus x to the n over h. And remember, this is just taking a limit as the difference quotient. That's the definition of derivative. So we're going to use this definition of derivative here. I was a little bit fast when I did that. And here we're going to use something called the binomial theorem. In the binomial theorem, what that says is that if you have x plus y to the nth power for n greater than 0 integer, that's going to be x to the n, n choose 0, plus n choose 1, x to the n minus 1, y to the first, plus n choose 2, x to the n minus 2, y squared. And this continues all the way out to n choose n, y to the n. Now, you might be saying, well, binomial theorem, where'd you pull that out from? Well, remember, n choose k is n factorial divided by n minus k factorial, k factorial. And this is what you get when you multiply this out. So x plus y to the first power, that's just x plus y. And this, of course, is 1 choose 1, and that's 1 choose 0. X plus y squared, that's, we know, is going to be x squared plus 2xy plus y squared. So for the binomial coefficient of 1 here, 1, 2, 1, right there. And let's do another one just to get the hang of it. Well, we know that's going to be x cubed plus 3 choose 1 plus 3 choose 2 plus y cubed. And let's just do one more. That's going to be x to the 4 plus 4 x cubed y. Now we get to 4 choose 2. which is 4 factorial divided by 2 factorial, 2 factorial. And you'll see that's 24 divided by 4, so that gives you a 6. Then we get 4 x y cubed plus y to the 4th, and so forth. And you can see Pascal's triangle appearing quite beautifully here. And if we want to do x plus y to the 5th, I know I'm getting carried away here. Let's use the triangle relation. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then the very last one is y to the 5th. So notice we get the triangle relation says that this number is going to be the sum of these two. That number is going to be the sum of these two. This number is the sum of those two, and so forth. I don't want to get too much into Pascal's triangle, but that's where you can get these coefficients from. So now let's go back to the derivative. So if we look at this as h goes to 0, x plus h to the n minus x to the n over h, using the binomial theorem, we have x to the n plus the first binomial coefficient is going to be n, x to the n minus 1, h, plus it's going to be n choose 2, x to the n minus 2, h squared. That goes all the way out to h to the n. Subtract x to the n over h. Now let's do some algebra. Now when we do the algebra, notice that this subtracts off with that, and we're left with this. N, x, n minus 1, h, plus n choose 2. Now I'm not gonna worry too much about what that coefficient actually is, because, and then I'll put some ellipses here. That's gone. We have this divided by h. Now, here's the key step here. We can factor an h out of every single one of these terms. The very first term I have x, n to the x minus 1, plus n choose 2, x to the n minus 1, h, plus a bunch of ellipses, h to the n minus 1. So I factored out an h out of every one of these terms. And notice, this h and this h can multiplicatively cancel. So we've now divided the h out. And this is a key step here. This is going to be the limit as h goes to 0. We have an x, n, n minus 1, plus n choose 2, x, oh, n minus 2 here, sorry. My bad. H, plus, I'll do one more here, n choose 3, x to the n minus 3h squared, all the way out to h to the n minus 1. Now notice, every single one of these terms, each one of these terms has an h. This one, there's no h. So when you let h go to 0, we're now in a position where we can take a limit by just plugging in, and all of these terms here, because you're letting h go to 0, all of these terms now are 0. There's no h here. So the actual limit we get is going to be n x to the n minus 1 as required. So that now this is proven. We've proved this. For n either 0, 1, 2, 3, any non-negative integer. So that's a big first step. However, that does not prove this for non-integers. So the next question is, what about for n negative? We have not done that. So what I'm going to do is I'm going to write, so suppose now we wish to take the derivative of x to the negative n, where n is not 0. So 1, 2, 3, etc. So what about x to the negative power? Now, there's a couple of rules we could do here. I'm going to go ahead and stick with the problem, but you can use the reciprocal rule for derivatives. So I'm going to write this as a limit as h goes to 0, or 1 over x plus h to the n minus 1 over x to the n over h. And remember, 1 over x to the n is x to the minus n, and 1 over x to the x plus h to the n is x plus h to the minus n. So if we wish to do that, we get the old common denominator. So at the top, we can now write this. We can get a common denominator. And the common denominator here is, we'll do it like this. And so what we end up with is we end up with x to the n minus x plus h to the n all over x plus h x to the n, x to the n. All right, now by using basic algebra, we now have this denominator here, and we have our h, and then we have the top. Now we can do the binomial theorem again. And we know this game. So the top is x to the n, and we do exactly what we did before, except now it's just the reverse of this. And so forth. And we've done exactly that right here. So by doing the same trick, and we don't need to belabor this, the x to the n's cancel, and we can divide out by an h. And this now gets a negative, because this is negative. So we now have an n, x to the n minus 1, plus n choose 2, x to the n minus 2, h to the first power. And this goes h to the n minus 1. And once again, the h's can multiplicatively cancel, like we have here and we have here. Now let's look at, now we can let h equal 0 safely, because there's no h in the denominator. So the numerator, we can plug in h equals 0 with no problem. So all of this goes to 0. That cancels, so we end up with a negative here, n x to the n minus 1. As h goes to 0, we now have x to the n, because this is now 0. And you can plug that in because You're not multiplying by 0. This turns out to be minus n x to the n minus 1. And this is now 2n in the denominator. And that's not minus n x minus 2n, my bad. And that turns out to be minus n minus 1. And that is the derivative of x to the minus n. So we have proved this for negative integers. Okay. So the next question is what about fractional powers? X to the p over q, where p and q are integers, possibly negative, where q is not 0. And that would be things like x square root of x and all this other stuff. Now here, what I'm going to do is I'm going to use implicit differentiation. Which does not depend on knowing what the derivative of a fractional power is. So what happens if you have this? What you have is you have x to the p. If you let this equal to y, that is exactly the same as x, well, up to domain. You can raise both of these to the qth power, and we have this derivative here. Now let's take the derivative with respect to x. Now this one, since it's now an integer, we already know what that is. This is now an integer as well. Times dy dx by the implicit function theorem. But notice, this is what we want. So we solve. So this turns out to be p over q, x to the p minus 1, over y to the q minus 1. And that's going to be dy dx. This is now equal to, well, remember, y is x to the p over q. So what we have right here is we have x to the p minus 1. The bottom here, remember, y is x to the p over q raised to the q minus 1. So now when we multiply this together, we have x to the p minus 1. The bottom, these multiply, right? So this, the bottom right here, let's just do this a little bit more carefully. When we multiply these powers, you multiply this power here. So that's x to the p minus 1 over q. So this is now x p over q, x to the p over q, sorry. Now we have x to the p minus 1. Now this is going to be another minus another p plus 1 over q. Right? So I do have, yeah, I got that. So, and let's go ahead and work this out here. Okay, so I have this, have that. Okay. Oh, yes, it's minus p over q. Yeah, when you multiply this together, we get this p here. So this works out to be p over q, x to the um, right here, p minus p. So we get p over q minus 1 as exactly we needed. These two p's cancel, and we still have this p over q that you get when you do this multiplication. So we now know this is true for rational powers. How about that? Now the fun begins. What about dx of x to the r, where r is real, not necessarily rational? In other words, r is pi, r is root 2, etc. Something that is not a rational number. Now here we need to use the following. We need that the derivative of e to the ax is a e to the ax. And we also need chain rules and stuff like that. So what we do is we write x to the r is e to the log of x to the r. Now, of course, that means x to the r has to be a positive number. And if you think about it, if you're going to raise something to a irrational power, you can get into trouble unless you want to use complex variables for negatives here. So let's just rewrite this as e to the r log x. And that's going to be x to the r. Now, when you differentiate, we get the derivative of e to the r log x, which is e to the r log x, multiplied by the derivative of the exponent. And the derivative of log of x, and we do need that here. So it's going to be r over x. Well, that is going to be x to the r times r over x, which is x to the r minus 1 times r. So now you might say that's cheating because we use the derivative of this, we use the derivative of e, we use properties of logs, but none of that, to my knowledge, actually requires knowing what the derivative of x to the r is for r possibly irrational. So this now gives us the proof. So what we've established up to knowing these extra things here, that the derivative of x to the r is rx to the r minus 1 for r real. Now, you didn't want to know that? Well, that's okay. Thanks for watching.